So depending on okay, you had we got the alkenes. So we're done with alkenes. Now we're going to alkynes. So we're going to step up. Okay. So let's start our discussion about alkynes. How do we name them? Well, alkynes are very similar to alkenes, not just in name. Well, not naming, but in reactivity and how we make them and use them. Okay. So alkynes not as prevalent as alkenes, but they do still have their uses, not only synthetically in the lab, but also as drug targets, or pretty much structures that are targets for pharmaceutical companies, molecular electronics, stuff like that. So it still has some appeal to be made. Okay, so naming here. Let's talk about naming. All right, for naming, instead of ENE, we use YNE. All right. And then just like alkenes, we number the end closest to what functional group? Say again. Which we number the end. We just had an alkyne in the chain. We're going to start numbering from where?
Is it a double bond or triple bond?
Yeah, the alkyne or the triple bond. Good.
But if there's a double bond, would you start there?
Oh, that's a good question. Yes, you would. You would start actually from the double bond. Okay, and we'll see some examples like that. In most cases, you may see a double and triple bond, but you may not see it, but sometimes you may. Okay, and so it's just good to be aware how to name it. Okay, so let's do an example. All right. All right. So we're going to number the end closest to the alkyne. So we start 1, 2, 3, 4, 5. All right. So how will I start naming this one? What's at the 4 position? Bromo. So we're going to start by calling this 4-bromo. And that's what's my other substituent? 3-methyl. You got it. Thank you. All right. And then we have to indicate where the alkyne starts. So what number should we put at the end here?
2.
2? Well, no. Where does it start in the chain?
1.
At the 1 position, right? So let's put the lowest number. It starts at the end. So it's a terminal alkyne, 1-pentyne. Okay. Another way you can name this is you take the same name, 4-bromo, 3-methyl. Okay. Then you can put the pent here. Then in dash 1-ine. Like we saw with alkenes and alcohols. You can indicate the number after as part of the parent name in this abbreviation type scheme here. Okay. Are any questions how we name that? Do we need to review any type of nomenclature? Are we comfortable with the numbering? The lowest numbers should go on the substituents, and then we list them alphabetically, starting with bromo or whatever substituent comes first in the alphabet.
Will you accept either name?
Yeah, either would be fine. Mm-hmm. I have no preference, so either one works in here. As long as you don't forget the numbers, don't mix up the lettering or mix up the naming. Like if you do pent-methyl, don't do that. you'll be fine. All right. So now if the alkyne is a substituent, we just, instead of alkyl group, we'll call it an alkyl group. Alkyl group. Yeah, try saying that 5 times fast. Okay, so if the substituent has a triple bond, they are called alkynyl. So it kind of sounds like you're saying alkyne groups. All right, so for example, let's say we have our cyclohexane. Remember, you find the longest chain in the ring or on the linear chain that extends from it. So remember here, these are actually 2 carbon atoms. So I'm going to put them as dots so it's clear to see that they're still carbon atoms. Okay, so what do we, so here you have a cyclohexane. Okay, so you have a ring here. So that's, you have a larger, sorry, let me see what I want to say. You have a more carbon atoms in the ring than if you just use the linear chain, right? So we're actually going to call this still connected to the 2 positions. So this one will be called, so the parent chain will still be cyclohexane. All right. And at this 2 position right here, okay, you have see at the 2 position here, you're attaching this 3 carbon chain. So this will be called 2-propynyl because it's a 3 carbon chain. So we make that like an alkyl group, but in this case it's a alkyne. So 2-propynyl, and that's because on the alkyne chain, it's at the 2 position, and it's 3 carbons long. So that's why it's called propynyl cyclohexane. Right here. Okay, but for the nomenclature, I want you to be able to name alkynes as if they were on the parent chain. Okay, so that's the thing I'm focusing most on. Okay, any questions about alkyne naming in general? Next, we're going to go to situations where we have both alkene and alkyne in the same molecule.
Can you give another example of that alkynyl group?
Yes. So, like, if I have something like this. Okay. All right. So we look at this, sorry guys, this screen, I don't know what's wrong with it. I'm trying to troubleshoot that too. So 1, 2, 3, 4, 5, 6, 7, right? So we have 7 carbons on the linear chain. Okay. And then this is 1 carbon and 2 carbons. All right. So right now at the 4 position, we have an F-dinyl group. F-dinyl. Okay. So 4 F-dinyl. Okay. And now what's the parent name? Heptane. Yeah. So let's put that in blue. So let me just show you that this group represents this substituent. So that's a substituent there. Okay, so whenever the alkyne is not part of the longest continuous carbon chain, it becomes a substituent, just like we saw alkyl groups. Okay, so hopefully that makes a little more sense there. You know what? Let me just run this back and let me just double check this naming. I might have I think I might read up on it a little bit more. Okay, so if it's different, I'll let you guys know next time. Because now just looking at this name, I'm kind of second guessing myself. All right, but this example, this is usually this is a good one. Okay, so for adenyl heptane. Okay, but usually here. The alkynes we'll see, they're part of the main chain, so they'll either be, they'll be part of the main chain, and that'll be the parent name as well, okay? But let me just double check on this example, because I might have gotten the name wrong, but I don't want to confuse you guys, okay? All right. All right. All right, now let's go over another example. We have now, what if you have both alkene and alkyne? So both alkene and alkyne in a compound. So that's definitely very common. So that's what we call, we combine the two names, alkyne. Okay. All right, you have two situations. You can either number from end closest to alkene or alkyne. Now, can we think of a situation where this might be a problem? What if they were both equal, right? What if they're both equally distant from each other, or if they have the same number from the end, okay? If you have the same number, we just tossed it up here. If same distance, this is probably not why, but they gave the double bond preference. Maybe because they're more prevalent in nature. Lower number. Okay, so we're going to give the double bond of the lower number. If they are equal distance, that means if you number from, they'll have the same number regardless how you, which end you number it from. So let's do an example here. All right, so this one. Okay. So no matter which end we start from, either the alkyne or the alkene will have what number? 1. So in this case, you want to number it from the alkene portion. So 1 hexane, 5 ine, because that's where the alkene starts, at the lower number, 5. Or you could do hex 1 ene 5 ine. So, unfortunately, these are the two only ways we can name this, and that's because both groups have numbers and they have suffixes like hexane and ine. So we have to name it this way. Okay, so they're both pretty much part of the parent name. So 1 hexene dash 5 ine or hex 1 ene dash 5 ine. Yeah, because it would make sense to say hexene, then hexine again. So it's a little jumbled if we say it that way. Okay. So if your double bond has geometry, remember E or Z alkenes, we have to specify that. So for this example, what kind of alkene is this? Is it a cis alkene or trans? Yeah, so the H's are pointing this way, right? So you see the H's are pointing in opposite directions. So cis, if it's cis, what do we call it? Z or E? Let's do Z. How about trans? Yeah. So these are based on the German words. So just remember, cis is for Z, and then trans is for E. Okay, but these has only two substituents, so you can use cis or trans as well. It wouldn't actually matter. So we have the E isomer. Okay, and then let's number it again. All right. Well, there's only one way we can number this one because the alkene is at the end. So 1, 2, 3, 4, 5, and 6. Okay, so we get E dash hex dash green, because that's the alkene, right? And then where's the position for the alkyne? Dash what?
1.
Yeah, dash 1. And then dash ein. Okay, are there any questions about how we named this one? So it goes with practice. Okay, so that's how you would name these substituents if you have both an alkene and an alkyne. But let's do one more where we introduce stereochemistry. I think it's useful if we find we also remember stereochemistry. Okay. All right. Do we remember R and S? All right. Okay. So, what kind of alkene is this? So, what kind of alkene is this? E or Z? Let's look at that double bond right here. So are the carbon groups, are they pointing, are they on the same side of the alkene or are they on different sides? Yeah, so the alkene, so this one's pointing up, right? It's going this direction. But this one is going this direction. So they are different. They are different groups. So this is an E alkene, okay? Now we got to specify the chiral center. Where's the chiral center here? Let me number it for you. Say it. 6. Oh, where are you numbered from? The alkyne? Oh, yeah, you're right. We do number it from the alkyne. Okay, let's do that. Because they're equidistant, right? Yeah. Oh, wait. Well, what takes precedence over the alkene? What else is in there?
The alcohol substitute.
Yeah, the alcohol. So let's look at the alcohol. So the alcohol actually takes precedence there. So 1, 2, 3, 4, 5, 6, 9. All right. So at the 4th position, we have a chiral center. Is it R or is it S? Let's see. Yeah. All right. So look at this way. Oxygen is 1. This is closest to the alkyne, so that's 2. And then dri is this carbon chain to the alkene. And then not shown is the hydrogen in the back. And that's number 4. So we go 1, 2, 3, and hydrogen is automatically the lowest substituent, so it has the 4, and it's in the back, so we name it an R isomer. So this is the R isomer. All right. So we can now combine these things. So since there's only one alkene stereochemistry and one stereoisomer position, we don't actually have to number it because it's automatic. So the chiral centers are, the alkene is E, and then let's name the rest of the molecule. All right, so we have a 9 carbon chain, so we're going to write non-7-ene. Okay. All right. At the 2 position, that's where my alkyne is. And then, how do I specify the alcohol? -4 dash, what's the ending for the alcohol? Yeah, O or OL. So see here, it gets a little more complicated once we have a lot more different functional groups in the molecule. So you ever looked at, a big compound and the IUPAC name, you'll see that it's like maybe a couple, maybe 50, 80 characters long. So it becomes pretty redundant to start naming these things and just come up with a brand name like Ozempic. You try to name Ozempic, I don't know if you ever looked at the actual formal name. It's like, I would say over 100 characters, 100 characters long. Okay, are there any questions about nomenclature? So this is the basic for nomenclature. Realistically, what I expected you to do on the quiz is not this stuff, but this. Use the normal ending, okay, right here. If you could do that, you're fine. Yeah, Catherine.
If we have multiple double or triple bonds, we still use the mono, like the di-tri.
Yeah, so you've got the diene, diene, right? That doesn't change. Yeah.
And that doesn't count towards the alphabet aspect, right?
No. That's just yeah. That'll probably be towards the end because it's like diene. Yeah. Right. Good. All right. Any questions on nomenclature? Alkynes, very similar to alkenes, and then still be able to name the substituents. Okay. All right, structure and bonding. All right, so here is what I wanted to come. This is why I talked about acidity, because we're jumping right back into some of these concepts, okay? We're now taking what we learned about reactions and then just increasing our knowledge of the reactions we see of different functional groups. So now let's talk about structure and bonding. All right. So one thing about alkynes, has anyone ever used an alkyne before? Anyone ever used a acetylene torch? That contains an alkyne. And the thing about alkynes, they typically burn hotter than most hydrocarbons. So alkynes have high heat of combustion. Okay, so let me just write the equation for you. So I have 2 alkyne molecules. All right. Okay, so any hydrocarbon reacts with oxygen. What are my 2 products in combustion? Water and? CO2, yes, thank you. So if I balance this equation, I should have 4 carbons over here because I have 2 acetylene molecules. Each of them has 2 carbons each, okay, and 2 H2O molecules. All right. Does anyone know? So if I have the flame here, so if I'm talking about acetylene flame, right here. Let me see. Let me write here. Let's write the delta H. Sorry. So the delta H for this reaction occurring once per mole. Okay, so for every 2 moles of acetylene, you get 622 kcals per mole. And if you ever heard of the acetylene flame, does anyone know how hot it can get? It's pretty hot. Let's see here. 3,330 degrees Celsius. So that's a pretty hot flame. Okay, so that's why it's used in like welding and in chemistry lab. It's used to flame dry glassware if your chemical reaction is sensitive to moisture moisture mainly. Okay. All right, so alkynes have high heat of combustion, so they make them particularly useful to generate a source of heat to burn. Okay, so one aspect is blowtorches, and then another one might be engines of some sort. Acidity. Let's talk about the acidity of alkynes. So previously we looked at alkanes. Alkanes are not very acidic. They're very stable. All right, so not very useful. But if we looked at one of these hydrogens, the pKa is around 50. So not very acidic at all. Virtually not an acid. We looked at alkenes. Alkenes are slightly more acidic based on the hybridization of the carbon. So remember the orbital in karyotype orbital plays a role in acidity, and that's the last option you consider. And since we're comparing both carbon atoms, the orbital matters here, so 44. So not that useful. But what's useful about alkynes is that the acidity actually drops considerably, and now it's in the realm of being deprotonated by a suitable base. All right, so this H is actually acidic. It has a pKa of 25. So we can actually use reagents in chemistry to deprotonate that and and make it useful. All right. Any questions about acidity or the structure and bonding? No? All right. All right, let's go over a few now. We're pretty much done with the concepts. What do you think's next? How do we use these guys? So reactions. All right. So preparation of alkynes. So let's talk about preparation of alkynes. All right. So how do we prepare alkynes? Well, we eliminate them to form. So we formed them by elimination of HX from vicinal dihalides. Okay, so I'll explain what that means. Some vicinal dihalide. All right, so we have an alkyne. All right, we have dihalide vicinal means they're on opposite or on adjacent carbon atoms, and you're going to use a suitable base to deprotonate and eliminate the halogen. So sodium amide. All right, and liquid ammonia. So you actually have to work with ammonia here. Okay, and then negative 33 degrees Celsius is the temperature you'll have to at least maintain to get liquid ammonia. Okay, so once you do this, you actually form the alkyne pretty readily. That's because you eliminate both the halogens, okay? So this is what we call an internal alkyne. There's no hydrogen atom. So it's internal alkyne here. All right. All right, I'll go over the mechanism, how exactly this works. If you remember, E2 type reactions, elimination, that's the mechanism that actually forms here. All right. Now, how about a terminal alkyne? The same kind of thing, except now you have, instead of a R group at the site of alkyne formation, you're going to just have an H. So there's going to be a terminal carbon atom here. And Br here, so still a dihalide, and you're going to form, but in this case you need, it's a little tricky here, you need 3 equivalents of sodium amide. Okay, and the reason why you need 3 equivalents is so that the alkyne can form in great yield, okay? And then 2 here is when you're going to use H2O to protonate the alkyne, okay? So I'll just put a little note here. You need 3 equivalents, so this reaction won't work if you don't have 3 equivalents. So this is by experiment, and you need to use 3 equivalents so the alkyne can actually form in solution. So 3 equivalents, so alkyne can form. Okay, and the final product here, you're going to get a terminal alkyne. Okay, so let's go over, let's see, what time is it? Okay, so let's go over the mechanism. How does this work? Okay. So now let's go over the mechanism. Of the preparation of terminal alkyne. Okay, so I'm going to draw this out like this. Br coming down like that. My 2 hydrogens, one of my hydrogens right there. And then I'm going to draw it kind of straight down like this. Br. And my other 2 hydrogens are like this. So I kind of drew it in the staggered conformation. All right, so NH2. So this reactive sodium amide, that's the reactive form of it. It's going to take one of these bromine hydrogens and then eliminate one of the bromine atoms on the opposite side. Okay? And then what do we get is first the sodium amide will turn into ammonia. Okay? And then the intermediate product here is going to be an H, the methyl group on the top left, an alkene, an H, and a Br. Okay. So that's one equivalent of sodium amide. So what do you think happens next? We need to form a triple bond. So what's going to happen here? Yeah, so sodium amide is going to come here. So I'm just going to put this, let's just put, negative sign. It's going to come and take another hydrogen and kick it off, form a triple bond, and then the bromine goes away here too. So bromine actually is a byproduct, but we just didn't show it. So we're going to leave it out like that. Okay. So what happens here now is that sodium bromide, sorry, not sodium bromide, but now we have the alkyne, triple bond, CH. All right, plus NH3. Okay. So the problem with this step now is that this hydrogen right here is very acidic. So you need to deprotonate it with another equivalent of sodium amide, just to ensure that all of the reactant has come over as the alkyne. Okay, so if you deprotonate this, you will. It's because sodium amide is going to react now with the alkyne here. Okay, so as this forms. So let me just illustrate something. As this forms, sodium amide can attack this, or it can attack another molecule of this. So if you have that discrepancy, to ensure that all the alkyne can form, you need to add a third equivalent of sodium amide. So that's what happens. So what happens here is that there's an additional step. So I'm going to take this. I'm going to rewrite this molecule. I'm going to rewrite this on the next line here. So let's take our alkyne again. Okay, so a third equivalent of sodium amide will come by and deprotonate the alkyne. Okay, so this step is very fast. So it's kind of like equilibrium. If you remove the product of one step, something that's in dynamic equilibrium, you're going to shift that equilibrium to replace the product, so that it will force the reaction to go forward to completion. And that's what's going to happen here. All right, ammonia plus our alkyne, negative charge here. So remember, the pKa of this alkyne is 25. Okay. And my pKa of water is 15.7. So what's going to happen to this water if this alkyne approaches the water molecule? Which one here is the stronger acid? Water. So it's going to donate its hydrogen, and that's how the alkyne gets reprotonated. So that's the purpose of the second step. So you get your alkyne. So it looks like a pointless step, but you just gotta believe me. If you don't do this, you won't get close to quantitative yield or complete conversion. So that's why you have to take that into account. All right. Okay. So let's rest on that for a bit. All right, you guys want to take a little break before we continue? Okay, sure. 10-minute break, 5-10-minute break. And then we'll pick up on making, how we make alkenes using, how you make alkynes more. Got it. Thank you. Cool. Oh, equal. Where you guys go? You didn't sign here.
Sign where?
In the box. So just sign right next underneath.
Okay.
I need that. It's so big.
Because I know you asked me if one to my cousin, one to like my other cousin. You didn't even notice that. And the rest of
We're gonna try to do the petition tomorrow.
All right, just keep me updated.
Yeah.
Okay.
Because otherwise it won't let us register.
I see.
That's one of them.
Okay.
All right. Okay, so let's pick up where we left off. So you notice here in our looking at alkynes, it's possible to make it negatively charged, right? So you can make it negatively charged. And so we could use this now to use it as a nucleophile to make, to lengthen the carbon chain. So that's one of the useful things for alkynes. So let's prepare preparation of alkynes. From alkynyl anions. Okay, so we have our R group, C, triple bond C, H. So we use a couple things here. So remember lithium reagents. They're also great bases, so we can use N-butene. So what this stands for, N-butene, is N-butyl lithium, okay? So N-butyl lithium, if I can write this on the side here, N-butene is this. 4 carbon atoms. And a lithium reagent is bonded to lithium, so it's a pretty reactive reagent. Remember, metal carbon bonds, they'll make the carbon partially negative and the lithium partially positive. So in organic solution, this will be acting as a good base. Okay, so this will be a base here, and then if we look at the second step is going to do a nucleophilic substitution reaction, like we saw SN2 type chemistry. And what happens here is your R group bonded to the alkyne is going to be able to add this 4 carbon chain here. Okay, so we see here, this is 4 carbons. 1, 2, 3, and 4. All right, so let me just break down what happened in the first step. So in the first step, step number 1, okay, you're acting as a base. So the alkyne forms the alkynyl anion here. Okay. So just like in this step, we had a base. You see how we had a base here? Deprotonate. Got hydrogen. The same kind of thing is happening here. This is going to be your base. It wants to take away a proton, acidic proton. Okay? And now we have a carbon atom with a negative charge. Carbon atoms are very good nucleophiles, right? So what's going to happen if it sees a electrophilic carbon atom? It's going to Rx. What did I put Rx here? Is that what I had Rx? Interesting. Okay. Here, Rx. So R prime, we're just going to make that equal to butyl. CH2, 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 CH3. Okay? So it equals this group here. All right? So if I have that R group, okay, what's going to happen here? As I have an alkyl halide, a good electrophile, and so partially negative here, right? And a partially positive charge here. So X can equal a halogen, chlorine, bromine, iodine, or OMS minus, or OTS, remember good leaving groups? So any of those will allow this transformation to happen, okay? So you're going to do an SN2 type reaction and kick off the X, and then you get to this reagent here. And I just made R prime as my alkyl group. So I just gave it an alkyl group, so you can see that we can actually add any primary alkyl halide to do SN2 type chemistry. Okay. Are there any questions like on those steps? What, how we got to that, the final product? So let's remember here, an alkyne, this is not very reactive, right? The alkyne here, not very reactive. But we can make it reactive by treating it with a base first. So that's pretty much how organic chemistry works. You make a reactive intermediate, and you can react it with something else, and you can actually build up the molecule like that. Okay. So that's one way to prepare alkynes from alkyl anions. You deprotonate with a base and do SN2 type chemistry with an alkyl halide. Okay, so there's two different reagents we can make. So let's try another one. This time we're going to use the same alkyne. So notice here, you can only do this with a terminal alkyne because you can't form an anion like this if there's no hydrogen there first. Okay, so we're going to do the same treatment here, N-butene. So that's our good base. And THF. Okay, so we get R. So here I'm going to write this as C minus, lithium plus. So that's my salt. So that in solution, I'm going to form this salt in solution. And then what I'm going to do next is react it with a good electrophile. So let's use an epoxide this time. So this time we can actually use an epoxide. So remember how epoxides work. Which side will this attack? Which side will the alkyne anion attack the epoxide? Is it the least hindered side or the more hindered side? Yeah, the least hindered. Remember SN2 type chemistry, right? Good. So I'm going to attack the least hindered side, so I'm going to go right here. Okay, so I'm going to open the epoxide like that. So we could draw that, those arrows. This side, and then I'm going to go up like that. Okay, and then eventually what we get here is R dash. So I'm just going to draw the alkyne now. Boom, boom, boom. Like that. Now I'm going to just draw it downwards. Okay, and then this is so this is that carbon. See, this is where the methyl group is. And here's the O minus. And then what's the last step do? Protonate it, right? I'm going to protonate the negative charge to neutralize the molecule. So now I can isolate the neutral compound, right? All right, so we can write H plus here. Oxygen is going to take that. And we isolate the neutral compound. Oops, sorry, let me clean that up. Okay, there we go. All right, so that's how you can also, so see here, we elongated the chain and added an oxygen functional group here. So that's how we can prefer to functionalize alkynes, okay? So those are two classic reactions to elongate an alkyne. So you can attack epoxides, add carbon atoms and an oxygen adjacent to the connection. that joined the alkyne, or you can add a carbon chain to the alkyne to make it more functionalized. Okay. All right. Any questions about those two examples? All right. Let's go over one more example of making a functionalized alkyne. So we use bases. So it doesn't matter which base you use. You could use a Grignard reagent or N-butene. You can even use sodium amide, the one we used before up here, as a base. You can use that too to make the alkyl anion or alkynyl anion. You don't have to use a N-butene or a Grignard reagent, but sometimes these are just more convenient to handle, so that's why we use it. But they're not necessary. It's possible that you can use sodium amide as well. All right, let's go to R. So same alkyne we've been using. All right, this time we're going to use a Grignard reagent. Remember, Grignard reagents are also great bases, so we can actually use them to deprotonate reagents. All right. So this one will form the anion of the alkyne, but also you will get the MgBr kind of coordinating there, like a salt, like we did with the lithium. Okay. And then this next step, we're going to treat it as a Grignard reagent. Okay, so it's still considered a negative charge there. 2. All right. All right. So remember, this carbon is actually partially negative. This magnesium is partially positive. Okay. So in the first step, where is this carbon going to attach to? If it's nucleophilic, partially negatively charged, it's electron rich. Where in this aldehyde is it going to go? So we have to look at this molecule here first. How are those two molecules going to attach?
Partially negative carbon of the alkene.
Yeah.
Attacks the carbon that's double bonded to oxygen.
Right, so look at where the partial positive and negative charges are. So we're going to draw the arrows being attracted to those partial charges. So we are going to attach it like that, just like we did in the epoxide case right here. Like that. Okay? So let's draw the result of the first step. We get R, C triple bond, C. So the magnesium bromide, it just goes away in solution. It kind of comes out as a byproduct after you work everything up, but it's no longer there. Okay, so the triple bond now is going to be attached. So I'm going to draw a bond. I'm going to put the oxygen group here, O minus. Okay, and then the rest of the aldehyde right there. All right. And then after that, the second step is aqueous workup. So you're going to have H plus. And the negative charge is going to pick up that floating hydrogen ion very quickly. So what you end up with is the protonated alcohol, alkynol. So it has an alkyne and an alcohol. Like that. Okay. Are any questions how we connected those two pieces? Does anyone want me to go over it again or maybe a different one? Any questions there?
I have a question.
Yeah, Captain.
So technically with the reaction that we just did,
Yeah.
we don't have an alkynyl anion phase really. We don't have like a step where we stop at that.
Oh, no. You mean like when are you referring to like when it's just before it even attacks to the carbonyl group, or?
Yeah.
No, yeah. So we're specifically forming the anion so we can actually like use it to connect two pieces. Yeah. So there's no step where it stops, like in preparation of alkynes. Right. Good. Yeah. So here we're taking a terminal alkyne and we're converting it now to a internal one, and that's how we get increased functionality there. Yeah, the surprising part, once you do this reaction, you actually can't go backwards. So the plan should be to carry this molecule to further construction of different bonds, I guess. Okay, so that's preparation of alkynes, okay? So the first homework does go over some of these synthesis type things, so you'll have practice going through these reactions, okay? All right, so let's do, now we got the preparation of alkynes. Now the step to kind of go through now is how do these alkynes react to form different functional groups where the alkyne is being transformed, okay? So let me just put an arrow here. We are no longer interested in making alkynes. We are now interested in reacting them. So reactions of alkynes. So I want you to kind of separate these two processes here, or these two kind of division of reactions. One is just preparation of alkynes, right, which we did here. We showed a preparation of internal and external here, just from simple haloalkanes, and then we were able to take a terminal alkyne and prepare them from alkynyl anions. So there's two flavors here, alkynyl ions, how we prepared alkynes from that, and then how we can prepare alkynes from a dihalide compound right here. So two different flavors there. So two different methods is what I should say. All right, reactions. So first reaction we have. So there's actually less reactions than alkenes, so it's not as many. So complete hydrogenation. Of alkynes. All right. So if I have an internal alkyne, what do you think happens if I use twice the amount of hydrogen gas compared to alkenes, and I still use a platinum or palladium catalyst? So this is platinum on carbon, so this is our catalyst. So what do you think is going to happen if I just use hydrogen and it's an alkyne instead of an alkene? What's the product going to be? Or what's going to happen to the double bonds? So Each double bond, or sorry, not each, not the double bonds, but the multiple bonds. So what's going to happen to the triple bond if I react each of them? If I add two equivalents of H2? Yeah. So my all these bonds here, this double bond, this bond, and this bond. They're going to break, right? And instead, I'm going to form bonds to hydrogen. So I'm going to do that twice. So I'm going to form H and H, H and H. Okay, so this will equal R, CH2. CH2, R. So I completely reduced my alkyne into an alkane. So I can't stop at the alkene. Not under these conditions. Okay? All right. So mechanistically here, you don't need to know the mechanism. It's very similar to the mechanism for catalytic hydrogenation of an alkene. The metal surface is your catalyst. It's your binding site, like an enzyme for your molecule. And then the chemistry happens there when the hydrogen gas interacts with the catalyst as well. So there's really no difference. The only difference is you're starting with an alkyne instead of an alkene. Okay, so adding hydrogen across the molecule twice. Okay. But they use hydrogenation in industry. If you ever a fan of margarine or those spreads like vegetable oil, or basically spreads like jam, not jam, but like that contain vegetables and like all those flavorings, they do partial hydrogenation of fats, and that's what gets made into food products. Okay. So you kind of soften up the fat, make it more easier to kind of dig out or, use a knife to cut into. So that's how they make a variety of like butters and stuff. So that's what they do in the food industry and why hydrogenation is important here. So let's talk about how can we stop at the alkene phase. So here's part B, hydrogenation. All right, so these have, this first one is called using a specific catalyst. That's called Lindlar. Okay, so it's made after the person who discovered this. Okay, so what is Lindlar's catalyst? So if you ever see a reaction that says alkyne reacting with Lindlar's catalyst. Okay. So I'll probably say Lindlar catalyst. If it says that, you can assume, okay, this catalyst is going to do something specific. It will stop at the alkene. So this catalyst has been designed to stop at the alkene stage, and because of the structure of the catalyst, it is stereospecific for the cis alkene. Okay, so you stop at the cis alkene. All right, but you might be wondering what is the structure of this catalyst. So I'll tell you like what's in it, what's the ingredients. All right, so Lindlar's catalyst is this. So Lindlar is a mixture of calcium carbonate, lead acetate. So this is acetate. So we use OAC to denote acetate, okay? And then the other portion of this is something called quinoline. So quinoline is this molecule. It's an aromatic ring of benzene, and a nitrogen heterocycle. You don't have to know how. Oh, sorry, I think I messed up. My bad. No. Oh, okay. My bad, guys. Let's erase this. Step back. Sorry. Okay. Like that. So you can see here when this binds to the metal, it might you can maybe kind of imagine that it will prefer. So when these things come together, they create a system or a catalytic system that kind of has reduced activity based on the metal that's in there and the other components of this process. So all of these are kind of a mixture here. So they're all combined. Okay, and when they combine, they have reduced activity, and that gives rise to a way to stop at the alkene stage. So cis alkene is where we'll stop here. Okay, that's where it stops. Okay, so let's go over the other method. So if we can make cis alkene, what do you think it will be useful? What other alkene do you think we would like to form from an alkyne? Yeah, the trans alkene. If we have cis, can we have trans as well? Yeah. Okay, so alkynes and the trans, for the trans alkene, it's going to be a little bit different, okay? So this is where you get the cis alkene. Now, to make the trans alkene, you have to use a completely different reagent. This is called sequential reduction. Okay, so what I mean by reduction, this is a 1 electron reduction. So I'm going to reduce the molecule 1 electron at a time. So that's called 1 electron reduction of alkynes. Okay, so what do I mean by that? Well, let's talk about first the balance reaction. Triple bond. Okay, so you're going to use it's either sodium or lithium. Okay, either one of those metals, and you're going to use ammonia. Liquid ammonia here. Okay, and the second step is a water molecule. So I want to emphasize here that this is just aqueous workup. So used as workup. All right. Not part of the mechanism. All right, so this is just used as a step to just isolate the final product, really. All right, and what we get here is the trans alkene, sorry. R. Oh, sorry, I should put a C there. Okay, so we get the trans alkene. Okay. So this one, though, there is a mechanism we should consult, because the mechanism actually it plays a role into like, how to understand how this transform. Well, if the Lindlar's catalysts, they're metallic catalysts like the palladium and platinum. So the mechanism are kind of similar to how alkenes work when you hydrogenate those. But let's talk about how this one works, okay? All right. So we're going to draw the alkyne. Like so, okay? So the first step, you have a sodium. All right. And just the regular sodium atom. Okay, maybe do I have here? Let's go to, it's not open. That's weird. So, in sodium, how many valence electrons does sodium have? 1, right? So we're going to put a single electron around sodium. So what happens here is your sodium is the reducing agent. So it's going to become oxidized and give your electron to the alkyne. So how I like to picture it, remember when we showed one electron movement using the fish hook arrows? So you're going to give this to the alkyne carbon. Now my carbon has too many electrons. I'm going to push this bond here up to this carbon, both of those electrons, and I'm going to get now a redox reaction where sodium has now been oxidized and my alkyne has been reduced. All right, so now I'm going to draw the alkyne and I'm going to show you what happens in this structure. So R. So now I'm going to align the orbitals of both electrons here. So my R groups are going to be opposite of each other. And now here, I'm going to have my single electron on the carbon atom that I've just added right here. That's where that electron comes from. Then this other carbon is going to have a lone orbital with the lone pair that I've just put back onto the other carbon atom. And on this atom, this carbon now has a negative charge because it's a carb anion. Like that. Okay? So what do you think the ammonia does? So my ammonia has a fairly acidic hydrogen. Okay. So what do you think the hydrogen is going to do? Am I going to protonate something? So let's take this negative charge. So remember, nitrogen is also partially negative. What's hydrogen going to be? Yeah, partially positive. Right. So I'm going to attack that hydrogen. Now kick off this nitrogen. So the reason why this goes at all is because this carbon is a better base than nitrogen ever is. So that's why it will look like that. Okay. So what do we get here? Let's go to the next line. NH2 negative plus. So now this has gained that hydrogen. So let's put it in red. We have gained this hydrogen. Okay. Now our double bond has formed. And now we're going to have just an orbital with a single electron now. Okay. Well, we're not done. We need to now form the alkene. We're missing a hydrogen and we're missing an electron. So what do you think is going to happen next? Yeah, just another transfer of an electron from sodium. So how this works is you put sodium metal in ammonia, and that forms the that help forms the reduction process. That's how it helps the reduction process. All right, so ammonia is a solvent. It can go back and forth. And what happens here now, okay, is that sodium, in the presence of an alkyne, it will donate its electron more readily to the alkyne than ammonia. So boom, right there. And we get sodium metal again, all right, plus H C. So why, if I were to ask you a question, why do you think, in this picture, let me just draw this first. So why do you think the electrons want to be trans to each other? Look at these electrons here. So see these electrons and these electrons? Why do you think they want to be trans? What would happen if they were cis? Or if they were right next to each other? Would that be stable or favorable? Yeah, it'll be unstable, right? The electrons rather be far apart, right? So that's why the trans arrangement is the best, and that's why that's the one that forms. Okay. All right. So now we have the last step. So what happens here? So you'll see here that water is not even used in the mechanism. Okay, so the negative charge on the carbon, the ammonia is the solvent and the source of the reaction. Because if you add water will destroy sodium. So that's why you don't use water and sodium together. And with ammonia and sodium, the reaction is not as great. I'm sure there's sodium and ammonia, they can coexist in solution. They won't react with each other. So that's why we use it. Okay, so H and H2. All right, so the negative charge here takes the hydrogen like we saw before. And now NH2 is formed, and what we get out of here is the trans alkene. Now we have the whole molecule. Oh, sorry, I forgot. Sorry, guys. Draw the carbon so it's more consistent. Okay. So what the water step does, it pretty much just neutralizes the sodium amide right here. So what the second step does, it reacts with this, and so you can isolate the product. So it's just as a workup procedure. So in every reaction, you could do the reaction, but the next step is to say, okay, how do I get my product? How do I isolate the stuff I want? What's the stuff how do I isolate this stuff to, if it's the end step of a synthesis, you have to isolate it, then submit it for testing or, other experiments, like in medicinal chemistry. All right. Are there any questions on the mechanism? So you're using a single electron to reduce the triple bond to a double bond. Okay. If anything, guys, remember that this process, what kind of alkene do we form? trans. So this is your tool here, your new way to make a trans alkene. Okay. Mechanistically, I would say this mechanism is fair game, to be tested. So please practice how this mechanism works. And I feel like if you understand the mechanism, you understand how the reaction works as well. Okay, that's always something I try. And then for these other reactions, for the metal-based ones, the mechanisms are very similar to the alkene version. So you really don't have to memorize anything or, remember anything new. Okay? All right. So that's our first reaction class, which is reaction of alkynes, hydrogenation, or, reduction of the triple bond. Okay. All right. Okay, let's see. Do I want to? All right. All right. So, what's number 2? So let me just reintroduce this topic here. Electrophilic. Do we remember electrophilic addition of alkenes? All right. So what was electrophilic addition? We had an alkene, right? And what did we add to that? So let's recall this. Addition of HX. So X in this case, let's just keep it simple. Cl, Br, and iodine. All right. So this works for internal alkynes. It does also work for a terminal, but we're going to just start our discussion on internal alkynes, okay? All right. So yeah, we have an alkyne here. And just say we have one equivalent, HBr. HBr, one equiv. Okay. So the problem with just one equivalent is that you will get a mixture of alkenes. So you will get this Z alkene. Okay. So the BR has higher priority than ethyl. So that's why this is called the Z alkene. We're looking at these two groups. Br on this side of the carbons, this carbon atom, and then this ethyl group here. That's why this is called a Z alkene. We'll just write it as Z alkene here. Okay. So you get about 60% of this. And then only 40% of the E alkene. You can't really predict the ratios. You kind of have to just go play by what you get by an experiment. Okay. So let's just write this thing, and then we're good for today. All right, so this is now the BR is on opposite sides. So the BR and this one on this side, the ethyl group here now has switched. That is our E alkene. And we get this in 40%. All right, next time I will go over the mechanism on how exactly this forms. It's very similar to how alkenes reacted here, so we'll recall how that works next time. All right, guys, thank you, and have a great 4-day weekend. Or 3-day weekend, sorry. If you don't have class on Friday.